All right, what's up, guys? So now we're looking at 10.3, which is actually going to take probability and tie it into all the area stuff that we've been doing. So here's the part where actually geometry comes to play with probability. So your first definition that we're going to have here is the definition area models. So area models can be used to represent simple probabilities. So whenever we're doing these probabilities, the whole figure that you have is going to represent the total. So that would go on bottom. And then the area of what you're trying to find, the area of the shaded part is going to go on top. So that would be your desired, which would go on top. So right here, either polygons or circles can be used to create area models for probability. So like this gives you a visual portion of it to help you visualize. So steps: divide figures into equally sized sections and then shade sections to show desired possibility. So that's what we're going to do at the first example. So let's go and look at this. So right now, example number 1, it says, what simple probability is represented by each of the following area models? Assume divided sections within a figure are equal to area. So right now, looking at this first one, we have a circle that you can see is divided into 4 different sections. And so there's 2 of those sections that are shaded. So the whole thing, all the pieces, is going to be 4. And then the 2 shaded portions are going to be 2. So that would just reduce to 1/2, which would be 50%. Okay? So the next one is a square, and you can see the square is divided into 4 equal parts, so 4 is going to go on bottom, and then only one of those is shaded, so that's going to be 1/4. So the probability of landing in the shaded area would be 25%. So now it looks like here we have an octagon, and it looks like it has 1, 2, 3, 4, 5, 6, 7, 8 equal sections, and 3 of those are colored. So there's going to be 3 out of 8 chance that you're going to hit one of the shaded areas. So 3/8 as a decimal would go to 37.5%. And then lastly, we're given another circle, and it looks like it is divided into 1, 2, 3, 4, 5, 6 different pieces, and 4 of those are shaded. So 4/6 is actually going to reduce to 2/3, which 2/3 is going to be 66%. So that's going to be a 66% chance, or a visualization of 66%. So let's go and practice this on numbers 2 and 3. So on number 2, it says, use a hexagon to split into equal sections to represent the probability of 1/6. So right now what I'm going to do is I'm going to draw lines connecting each one of these vertexes here. And if you see here, we now have 6 equal sections, sort of, by my drawing, but just say they're all equal. And we want to represent 1/6. So if you look, there are 1, 2, 3, 4, 5, 6 pieces. So I'm just going to shade one of those. So whenever I shade one of these, this is now an area model representing 1/6. I know this is a terrible shade job, but who cares? You guys get the gist of it, okay? So now number 3, it wants to use a rectangle to split into equal sections to represent probability 0.8, which is also 80%, which is 8 out of 10. So 8 out of 10 will reduce to 2/5. So I'm going to cut this rectangle into 5 different pieces. I'm going to do my best to get this as even as possible. So there goes 1 piece. There goes 2 pieces. There goes 3 pieces. There goes 4 pieces and 5 pieces. And now 4/5 would represent 80%. So I need to color 4 pieces of these to represent 0.8 or 80%. So there goes 1. There goes 2, there goes 3, and there goes 4. So that's 4 out of 5 pieces would represent 80%. So these are just some quick examples of how area and model can work here. And so now let's go ahead and move into the math portion of it. So right now it says in example number 4, what is the probability that a randomly dropped counter will fall inside the trapezoid? So remember, what you want is going to go on top, and the total is going to go on bottom. So right now it looks like we have a square on the whole thing in my total. So it is 10 spaces across and 10 spaces down. So the total area of this guy is going to be 10 times 10. So that's going to be the total of the whole thing. And so now on top, we want the piece to fall in the trapezoid. So we need to put the area of a trapezoid on top. So remember, the area of a trapezoid is 1/2 the height times base 1 plus base 2. So let's plug in everything we need. So 10 times 10 is 100. We already know that. And so the height of my trapezoid is going to be here. So that's going to be 1, 2, 3, 4, 5, 6 spaces. So the height is 6. base 1, which is going to be this guy, is going to be 1, 2, 3, 4, 5, 6, 7, right? 7 across. 1, 2, 3, 4, 5, 6, 7. So base 1 is going to be 7, and base 2 is going to be 1, 2, 3. So base 2 is going to be 3. So now let's just plug in my numbers. So 1/2 the height, which is 6, and then base 1 plus base 2 is going to be 10. So 6 times 10 is 60. Half of 60 is going to be 30. So 30 over 100 is going to be the probability of landing in the trapezoid, which obviously is going to be a 30% chance. So there's a 30% chance if I randomly drop something on this piece of paper, there's a 30% chance it's going to land inside the trapezoid. So again, we're going to take the area of what we want and put it over the total area, and that's going to give me my probability. Another way of looking at this is by using degrees here. So right now, if you look here, it says after Gerald finishes homework, he must play a game of chance to determine how he will spend the rest of his evening using a spinner below. We need to determine the probability and percent of his spending the evening in each of the following events. So sector A is playing with your younger sibling, or sector D, playing in a band in a friend's garage. So we know on this spinner, in degrees all the way around is 360, so that's obviously going to be my total. So right now for sector A, if we look all the way across this guy, this is going to be a diameter, so that's halfway of the circle. So if this section, sector D, is 30 degrees, this right here is going to be 160 degrees. Nope, not 160, I'm sorry. It's going to be 130 degrees. 150 degrees, wow. It's going to be 150 degrees. So then to figure out the probability of him getting in sector A, you would then do, so I'm going to put A, all I would do is 150 degrees over 360 degrees. And then I would just find the decimal or reduce the fraction, and it would give me my percentage. So right now, if I did 150 divided by 360 as a decimal, that would give me 41% approximately. So now for sector D, if we look, I have 30 degrees, and that's going to be out of a total of 360. So 30 out of 360. If I did 30 divided by 360 as a decimal, that would be 8.3%, or I'll just put 8%. So there's an 8% chance that he's going to get in that section. Okay? All right. So on number 6, it says, at a school fair, students were challenged to hit one of the small congruent equilateral triangle regions at the large equilateral triangle board below with a dart. We need to find the probability of hitting a small triangle if the dart hits the large triangle region. So right now we're basically throwing a dart at this triangle, and we want to hit one of the smaller ones. So each one of these are equilateral triangles, and they're going to be equal. So we need to find the total area of the triangle, okay? So right now, what we need to do is we need to find the total area of the triangle. So right now, 1/2 the area of the base, or base times height, not the area of the base, that was my fault. It should just be base times height is the area of the triangle. So right now, if we look, 12, 6, and 6 is all going to add up to 24. So the base of my triangle here is going to be 24. So automatically, instead of putting B here, I am going to put 24. And then the height of my triangle, if I did this, this is going to give me a 90-degree angle. So this would be 12, that would be 12. And to find the height here, my height would then end up being, the H is going to end up being 20 point, I'm going to round up here, is going to be 20.8. So that would be the height of my triangle. So down low, that would end up giving me the total area of my triangle. Now what I'm going to do is I'm going to find the area of one of the smaller triangles and multiply it times 3 because we have 3 triangles, right? So I would end up doing 6 squared minus 3 squared, and the height of this guy is going to be 5.2. So I would end up doing 1/2. The base of one of my smaller triangles is going to be 6, and I'm going to multiply that by 5.2. So that's going to find the area of one of those, and so I'm going to multiply this guy by 3 because there's 3 of those triangles. So if I ended up typing this whole thing in the calculator, so 3 times 1/2 times 6 times 5.2 over half times 24 times 20.8, and when I click enter, there is going to end up being an 18.8 0.75% chance that if you threw a dart at this triangle, it would hit one of the smaller sections. So again, I did the desired outcomes, so this is the desired, over the total outcomes, and I'm just using area to find that. Okay, and then lastly on number 7, we just have some compound probability problems that'll help you figure out stuff. So it says, in the United States, approximately 2/5 of the people wear a seatbelt while driving. If 2 people are chosen at random, what are the following probabilities? So on A it says, what is the probability of both of them wearing a seatbelt? So we know 2/5 of the people in the whole world wearing a seatbelt. So the first option, we want them to wear a seatbelt, and the second option, we want them to wear a seatbelt. So 2 times 2 is 4, 5 times 5 is 25, and then 4 over 25 as a decimal would be 16%. So there's a 16% chance that you would find 2 random people that wear a seatbelt. B, only one of them wears a seatbelt, so that means only one of them. So let's say the first person wears a seatbelt, but the second one does not. So there's 3 out of 5 left. 2 times 3 is 6, 5 times 5 is 25, 6 over 25 as a decimal is going to be 24%. So there is a 24% chance that if you pull 2 random people out of anywhere in the United States, one of them will wear a seatbelt and one of them would not. So now in the last one, both of them are not wearing a seatbelt. So I'm going to do 3/5 times 3/5 because that represents 2 people not wearing a seatbelt. 3 times 3 is 9. 5 times 5 is 25. 9 over 25 as a decimal is going to be a 36% chance. So there is a 36% chance that if you pulled 2 random people out of the United States, 36% chance that both of them are not wearing a seatbelt, which is actually kind of bad because this is higher than all the ones that had a seatbelt option. Not a good thing in the United States. All right, guys, good luck with your practice.